so this is the third lecture on section 9.2, and I hope it's going to be a short lecture. So we're going to give first another application of Gauss's lemma to determine certain numbers to be primitive roots for some primes. All right, so this is theorem 9.7. And it says that let P and Q, which is 2P plus 1, be both odd primes. Then we have negative 2 to this power, or actually we separate it into this, minus 1 to t minus 1 over 2 multiplied by 2, which is the same as negative 2 to the, no, actually it is not. It's just because an alternating sign is a primitive root of a q. This is equal to t. All right. So this means that we're going to show that actually the order of this integer is going to be phi over q. All right. So here's the proof. We're going to start with considering actually two cases for the form of the prime p. We're going to consider two cases. P is congruent to 1 mod 4, and this is going to actually give us that for this it's going to be positive 2. And the other case where P is congruent to 3 mod, and that's going to give us negative 2 for the primitive. All right, so let's just start with the first case, case 1. P is congruent to 1 mod 4, which makes P equal 4k plus 1 for some integer k. And in this case, the negative 1 to the P minus 1 over 2 times 2 will be negative 1 to 4k plus 1 minus 1 over 2 times 2. And it's going to be 2k times 2, which is equal to 2. All right, now we know that the order for this case, the order of 2 to the prime 2p plus 1, which is a q, is going to be divisible by phi over q. All right, and for this is going to be, because it's a prime, it's a q minus 1, which is going to be 2p. Now, since 2 and p are primes, then the possible value of the order of 2 relative to q, or mod q, is going to be either 1, 2, p, or 2p. Well, I claim, or I'm going to show that the first 3 possibilities, these are not possible. Not impossible for Q to have these orders. All right, we're going to do one by, case by case. And we're going to do the same kind of analysis in the the second case where P is of the form 4K plus F3. Right? So for 1, okay, so let's look at the possibility that the order of 2 is equal to 1. Again, this would imply that 2 to the 1 is congruent to 1 mod PQ. And this would imply that the Q, which is an odd prime, is divisible by 1, and of course this is a contradiction. All right, the other case, if the order of this is equal to 2, this implies that 2 to the 1 is congruent, 2 squared is congruent to 1 mod Q, and this would imply that Q is going to divide by 3. But again, this is a contradiction because Q, this is a contradiction since Q is equal to B plus 1 and D, because it's an odd prime, so it must be bigger than or equal to 3. All right? In other words, Q is going to be bigger than or equal, so you put it here actually 7. All right, so it doesn't differ. All right, now we end up with a little harder case to prove that it doesn't, and that is for the P. All right, and to do this, we're going to do something different. We're going to be using Gauss's lemma, of course. Now we know that we have 2 over Q. This is equal by or congruent by Euler's criterion. We have one hand, this one is congruent to 2Q minus 1 over 2. And we do the calculation for this where the Q, this becomes 2 to the P. All right? Mod, of course, Q. Now, we have a Q, which is as this form, 2P plus 1. And this is of the form, all right, which is Q is congruent to 3 mod 8. In other words, we can turn it into a different kind. Now let's see what this in here. Remember that this means that the Q is going to be 8K plus 3. And we can write this as 2 times 4K plus 1. This means we have 8K plus 2 plus 1. All right? And this is, of course, is 2K prime plus 1. Or it has the same form, and in here we're requiring that, of course, the K prime to be a prime. Here, K prime to be K prime to be prime. When it is a prime, so it is a Q of this form. Then by actually theorem, which give us the quadratic character of 2, all right, which is theorem 9.6. It tells us for this kind of prime, 2q is going to be equal positive 1. Actually, this one is give us a negative 1. All right, since the q has this form, k8k plus 6. All right, well, let's look at now what happens if the order so now we have this. We already proved that 2 to the p is congruent to -1. Sorry, we have 2 over q. We go back to this. We have 2 over q. Remember, this is by Euler's criterion. We have this is congruent to 2 q minus 1 over 2, which we say this is nothing but p mod q. All right. Now, together with what we have in here, we also have this last congruence, which says that 2 over q is actually equal -1. So this implies that 2 to the p is congruent to -1 mod q. And this in itself implies that that the order of 2 to the q cannot equal to p. All right? Because when we raise it to the p exponent, we're going to come up with -1. So we're going to come up with 1. Okay? Because we cannot have this to be congruent to both -1 and 1, since 1 is not congruent to -1 mod q. You cannot have both of these. All right, so we are left with only one possibility for the order of 2, and that is the maximum kind of allowed order. So therefore, the order of 2 mod q is equal to p, and this is p of q, and this means that 2 is a primitive root of a q, which is 2p plus 1. All right, let's look at the second case, which I said it's similar, where the prime p is of the form 4k plus 6. Case 2, p is congruent to 3 4. So in this case, p is going to be 4k plus 3 for some. Okay. And let's look at this integer. So this is going to give me -2, actually. So this is 4k plus 3 minus 1 over 2 times 2 minus 1. So 4k plus 2 over 2, so this becomes 2k plus 2, which is negative. All right. Similarly, we gonna look at the order mod q of -2. We know that this divides again phi over q, which is equal to p, and again give us this order is either 1, 2, P, or 2. Same possibility. Let's calculate again negative 2 by Euler's criterion. This is congruent to negative 2 to the, so it's going to be to the P, okay, which is Q minus 1 over 2. And so this one is mod. Again, for the first two, so we're going to show that these are, again, these are impossible. These are impossible. Value for the whole. For 1 and 2 is the same sort of thing, okay? Means that you take the order, you assume of negative 2 is equal to 1. This implies that negative 2 to the 1 is congruent to 1 mod Q. And again, this is going to lead to Q divides negative 3. And you see this is not possible just because of the form of actually Q. Which is 2P plus 1, and look at what the T looks like. Similarly for 2. So it's going to give these little bit of details out. So let's look at now evaluating the Legendre symbol in a different way using Gauss's lemma. So we have negative 2, 2. Can write this is as negative 1 Q times 2 by Q. Now again, since Q is of this form, this has the form which is 8K plus 7. Okay, the other form. All right, and to see this, it's again the same kind of thing in here. If you take a factor of 4 out, so this becomes 2Q plus 1 plus 3. And this is the form of the Q in this case. And now by these two theorems that give us the quadratic character of negative 1 and 2, right, by theorem 9.2, we have negative 1 over Q. For this kind of primes, okay, so this one is actually negative 1. Okay, since Q over 4J plus 3. And by theorem, which is Gauss's lemma, actually, one of the applications of Gauss's lemma, theorem 9.6. We have 2 by Q. This one is actually positive. So these together, therefore, we have negative 2 over Q is going to be negative 1 times positive 1. So this one is negative 1. Now, remember also we had from Euler's criterion, we have this one was congruent to negative 2 to the P mod Q. So these together, we can see that going to give us the negative 2 to the p is congruent to negative 1 again. So therefore, negative 2 to the cube is going to be congruent to, or just the, actually, the negative 2 to the p is going to be congruent negative 1 mod cube, and which makes the order of negative 2 cannot equal p. So we ended up with one possibility for the order. Must be equal to p, which is 0. And this makes negative 2 is a primitive root of p. All right. So this will take care of the second case. Now, theorem 9.8, I did prove this one is actually the second part of or lecture on section 9.2. Now I want to give another version of Gauss's lemma, which actually makes the computation of Legendre symbol easier. All right. Now let's recall the Gauss's lemma, the first version. Okay. So Gauss's lemma. So this is first. I want to put it briefly. I don't want to put all the details in here. So we have p is an odd prime. A is an integer, relatively prime to b. Then it says that the quadratic character of A relative to or mod B is, this is given by negative 1 to the n, where n is the number of least positive residues mod p of the integers or of the integers in the set S in the set S, which consists of A, 2A, and so on, up to B minus 1 over 2. Or remember, we use the word instead of residue, the remainders, when we divide the elements of S by B, and such that these residues, let me call them R sub I. Okay, so these residues such that R sub I is actually, it's going to be bigger than, actually S sub I. See, these are we call them S. S sub I. All right, the S sub I's are bigger than P over 2, and of course they are less than or equal P minus. All right. So in other words, when we want wanted to calculate, okay, the Legendre symbol in here, we are really not interested in the exact value, all right, of n. All right, all I need is actually the parity of n. Means if it is even or odd, then it will determine we get a positive one or a negative one. So there is no need to have exact value of n. Just we need to know if n is, or we just need to know if n is even or odd. So in other words, what we need basically is to know n mod 2. So this is equivalent to have n mod 2. If n mod 2 is equal 0, then n is even. If that one is equal to 1, then n is odd, and then we can determine the character of of A, quadratic character of A. And this is what the next theorem is actually, or the second version of Gauss's lemma actually just gives us, right? So let me put the statement. This one is actually let me put it's called lemma in the book, and this is, we call it the second. Of Gauss's same assumption, of course, that the order prime and A an integer relatively prime to P, and we're gonna also need if n is the number of least residues of least positive, as I described it in the first actually lemma, or here the least positive residue. S sub I of this set of the integers S, well, A to A up to P minus 1 over 2A mod P with such that these SIs are going to be bigger than P over 2, but they are less than or equal to P minus. All right? So these are the assumptions. Then N is congruent to this quantity, k equal 1, p minus 1 over 2. So this is index of the summation. The greatest integer of Ka over P mod 2. And hence, this gives us, as we're going to discover, that A by P is equal -1 to this exponent. Because this just give us positive, even odd. Equal 1, p minus 1 over 2 of this bracket, Ka over. Well, so the crucial thing in here is this number right here. What kind of number is it, even or odd? All right, we're going to go ahead and do the proof for this. So let's start it from the top. The proof. A typical element from S has this form. K sub multiplied by A, where K ranges between 1 and P minus 1 over. All right. Now we're going to apply the division algorithm by the division algorithm. We know that I can write the Ka is equal the quotient is equal to Q sub K times P, we're going to divide by P, plus T sub K, which is the remainder, where the T sub K, which is the remainder, is bigger than or equal to 0, but less than P. All right, now if I divide this by P, so we get Q K plus P K over P. And remember, this is true for every K in here with the 1 and P minus 1 over. And in this case, of course, where 0 is less than or equal to P sub K, less than P over P over P, which is 1. Now, by taking the greatest integer function applying to this equality, so the greatest integer, Ka P, is equal Q sub K plus P sub K over P. But since the fractional part, which is P sub K over P, is less than 1, so we end up with the bracket on this side is equal just to Qk, just the integral value of this quotient. All right? So in other words, we can write every element, K sub A, or Ka, in S in this form. So this implies that the elements in S can be written as this. K sub A is equal, we're going to replace the Q sub K by the Ka over P times P plus T sub K. Again, where the T sub K between 1 and less than, or less than or equal P minus 1. We could actually put. All right, now we're going to recall the two sets that we are actually used to partition the S. And actually, the argument goes by just kind of repeating what we've done earlier, okay, on the first proof of Gauss's lemma. All right, so we're going to recall the sets. A, which consists of the least positive residues or remainders. When we divide elements of S by P, we call them R1, R2, R sub M. All right, and P, which is equal S1, S2, up to Sn. So this is where the N goes in here. Where the R sub i's are the residues or remainders, residues mod P that satisfy of elements, again, of the elements of the integers in S, okay, such that the R sub I are less than P over. Similarly, also the S sub i's, we put it in here, the S sub i's are the same as this, except in here the S sub i's, S sub i's going to be bigger than P over 2, and they are less than or equal P minus. All right. Now, in other words, with this formulation in here, using the T, so this implies here T sub K is actually less than P over 2, then the R sub, because this is sub I here maybe, okay? If this one is actually less than this, then the T sub I is going to be equal R sub I. And if the T sub I is bigger than P over 2, then the T sub I is going to be equal S sub I. Here is for some I, of course. And this one is this. Now also remember that this set, which we have R1, R2, up to Rn, we will combine these and subtract the SIs from P. This is the same as, don't need a new proof because this is really the same argument as 1, 2, up to P minus 1 over 2. these are the same sets. Now we're going to apply the sum. Okay, so remember these facts, the sign and so on. So let me go in here. So I want to take the sum of this formula. Yeah, we're going to do the sum. We're going to take the summation, k equal 1 up to p minus 1 over 2. All right, okay, so A, this is going to be the summation of k equal 1, p minus 1 over 2, k A over p, p plus t sum. Now, in this summation, remember that this one, it could be either R or it could be S. All right? So we're going to take the summation. I'm going to separate these into the summation over those that give me R's and the one that give me S. Okay, because this is depending on if the T sub k is less than p over 2, that's going to go into this set. The other ones is going to go to this set. All right? So this altogether, it's going to be equal to k equal 1, p minus 1 over 2, ka over p, plus the, and I'm going to separate the summation in here because this one is going to be actually k equal 1 to m, and this one is k equal 1 up to n s sub. S sub. All right, now let's look at what also we know there about the two sets. All right, this set, which we just wrote in here, R1 up to Rm, and then P minus S1 up to P minus Sn. This is the same as 1, 2, and so on, up to P minus 1 over. So when we add up the elements in these two sets, we're going to have them equal to each other. So that's what we're going to do. We're going to do the summation. And then we're going to compare the kind of the two ways we sum up the elements in S. So we're going to do the summation for these. So the summation k equal 1 to m r sub k plus the summation k equal 1 to n of p minus S sub k. This is the summation of just k equal 1 to p minus 1 over, which is the summation of t. All right. So let's simplify this. All right. So this gives me summation k equal 1 m r sub k. And I can separate this into two summations. One for P, one for the SK, and then the other side, 1 up to P minus 1. This term right here, which is adding the number P to itself, basically n times, is going to give me NP. Okay, and the other parts, we're going to write them as S. R sub k plus, and then minus SK k equal 1 to n, and this is equal summation k equal 1 p minus 1 over 2. Now we need to put I should have labeled actually the equations that I have. First one, I will rewrite it again. And I'm going to call this is actually equation, this is number, we call this is number 2. Okay? And the first equation that we have earlier, so we also have this one, Ka, all right, K equal 1, P minus 1 over 2. This was equal to K equal 1, P minus 1 over 2, Ka over P, P plus the S sub, the R sub K, and the S. We call this is equation 1. Then I'm going to subtract actually equation 2 from equation 1. Okay. And we're going to rearrange the, of course, the elements. So we're going to go, going to take equation 1 minus equation 2. This would imply this. So let's go with the K summation Ka K. Actually, equation 1, yeah. So this is equation 1, K equal 1, P minus 1 over 2. And then minus, I want to use actually the this side I'm going to put it in the front. So I'm just going to have that one subtracted from the left. So K equal 1 up to P minus 1 over 2. At least these match with the summation index. I'm going to combine them. And this is equal to, so we're going to subtract, so we're going to write these down, minus the one in this side. So this is all put together, K equal 1 up to P minus 1 over 2, and Ka over P, then the plus. But as you can see, maybe you could make our life easier. So we're going to see that this one and this one is going to cancel, and this one and this one are going to cancel. So we end up with just minus, okay, because minus and okay, because you're subtracting 2 from 1. All right, we're almost there. Now, the left-hand side, we can simplify this by taking the, actually, we're going to have A minus 1, all right, and then summation K equal 1, P minus 1 over 2, just like it, all right? So when you distribute the summation, you get the first one and then the second summation. And this is equal to summation K equal 1, P minus 1 over 2, Ka over P minus N. Now we're going to look at what is the P looks like. Okay, now since P is odd, then P is going to be equal to L plus 1. And also, and A Let me see in here. There's one other thing I need in here. All right, so we have P is prime, sorry, is an odd, and this implies that P is going to be congruent to 1 mod 2. We also have, since P and A are relatively prime, this also implies that A is going to have the same remainder, which is 1 mod 2, sorry. All right, now we're going to take this equation here, we're going to take it mod, we're going to turn it into mod P. Sorry, mod 2. Mod. We're going to turn it into not actually kind of equality, but into a congruence equation. So the A minus 1, this becomes congruent to 0 because A is congruent to 1, so this becomes 0 times K equal 1, E minus 1 over 2, okay? Congruent to the other side, the P, NP is going to reduce to the following, so we can take a P out of these, so let me take P out between these, and then we're going to have the summation K equal 1, E minus 1 over 2, Ka over E minus N. All right, so this side is 0, of course, this side is 0, so now we're going to separate these into two sides. So this leads to saying that N is congruent to actually I want to change the P here. I want to change the P to 1. So I'm going to take in mod. Yeah, so this is just 1 in here. So we have now the N is congruent to summation K equal 1, P minus 1 over 2 of just the greatest integer. And this is mod. And this is exactly what we needed to show in the first part. Now for the second part, let's write this into, again, back to an equation. So we're left with to show, so this is what we need to show, that A by P is equal -1 to the summation K equal 1, P plus 1 over 2 of K A over P. To do this, remember that we have A by P like this. This is equal -1 to the N. All right? But in here, the N is not equal. It's actually a congruence. It satisfies a congruence relation. But we can turn this into N is going to be equal to 2 times R. In other words, change this into an equation. So this on the left divides the difference between the summation, all right, of QA over P minus N. All right, so we're going to turn this into 2R plus the k equal 1 to p minus 1 over 2 ka over. Now we're going to put this back in here. So we're going to make this as an exponent, and this becomes negative 1 to r multiplied by negative 1 to the summation of bracket ka. But the first factor is equal to positive 1, so this is equal to positive 1. And then we have the Legendre symbol given on that form. Now let's see how easy it is now actually to do calculation with this by looking at an example. Of course, we finished the proof here. All right, so let's look at an example. There's an example. Let's calculate or find the quadratic character of 5 mod 30. This is equal to. First of all, we need p minus 1 over 2. So this is going to be 6. And now we need to calculate, all right, these k a over 13 for k equal 1, 2, 3, up to 6. All right, and then we're going to add them up, basically, right? So we're going to go with finding these values, and then we're going to add up 1 to 6 of k over 3. So it's going to be the first one is the ace is 5 here, of course. So this is 5k, like this. All right, so it's going to be 5 over 13 plus 10 over 13. And the next multiple is going to be 15. And so on up to the last one, which is 10. Third one is, it's a fraction, is equal to 0. This one is 0, this one is 1. And then the other two values is going to be 3 different values, 1, 1, 1. And the last one is 2. Okay, 30 over 30 is 26, and the remainder, so it's going to give us actually multiple of 2. All right, so all together, this gives me 5. And now we have the Legendre symbol. It's going to be negative 1 to the 2. Now remember, this is not n. This is n mod 2. And this is, of course, all we need is to give us this is as a negative 1. Which you can, check by using Euler's criterion for using the first version of the number. All right. So this is the end of this very long section, section 9.2. Fortunately, the next two sections are much shorter than this one. And in section 9.3, we're going to be talking about the famous and most important, one of the most important theorems in number theory, and in particular in this course, is the quadratic reciprocity. Okay? So I'm going to stop right here.